Our next application of equilibrium is to acid-base chemistry. Some of those possible examples are shown here. The different cleaning products we have, the foods we eat, the medicines we take, the molecules in our own body, all have acid-base properties, and so these equilibria are relevant in all applications of chemistry. This is our key application of equilibrium to these acid-base reactions. It turns out this is a particularly good case to study equilibria because acid-base reactions are typically very fast. So we don't really need to worry about the kinetics. They reach equilibrium very quickly, and we can just concentrate on those equilibrium concentrations. Starting point for chemical equilibrium is the idea that even water, when it's as pure as you can possibly get it, has small amounts of these two ions, H3O plus hydronium and OH minus hydroxide. Small amounts of these ions in water have dramatic effects on the chemistry in water. The taste of a product, the rates of many different reactions, the particular configuration of molecules in your body, all governed by even very small concentrations of these two ions. As a result, there's been many different definitions of acids and bases that have helped us categorize this range of behaviors. Arrhenius's definition is sort of the oldest and first definition. An acid is something that increases the concentration of H3O plus ions, hydronium. A base is something that increases the concentration of OH minus ions or hydroxide ions. In this class, we're going to, of course, use this definition, but most importantly, we're going to use this Bronsted-Lowry definition. The Bronsted-Lowry definition states that an acid is an H plus donor. H plus, a hydrogen atom without any electron, is just a bare proton, so we call this a proton donor. Base is an H plus or proton acceptor. There's also this even broader definition of an acid as an electron pair acceptor and a base as an electron pair donor, which will be more relevant to you if you go on to take additional chemistry classes. It turns out that usually when water is the solvent, these three definitions are equivalent. So let's see how that looks for HF. Here's an example of HF in water. So we have water here reacting with HF. And again, the Arrhenius definition says that HF is hydrofluoric acid. It's an acid because it will increase the concentration of H3O plus in solution. Again, we could think about that in terms of, say, Le Chatelier principle. The more HF we put in solution, the more this reaction will shift to the right, and therefore the more H3O plus we will make in our solution. So HF is an acid for that reason. Now, the next definition for Bronsted-Lowry, when we look at the reaction HF here, the hydrogen is donated from HF, the acid, to H2O, the base. So since HF donates that proton, it's the acid. Since H2O accepts the proton, it's the base. And this broader definition of the Lewis definition also matches. HF accepts the lone pair and H2O donates the lone pair. And again, this example shows us some key principles of acid-base chemistry. All acid-base reactions are a reaction between an acid and a base. And according to this Bronsted-Lowry definition, every acid-base reaction is the exact same type of reaction. An acid donates a proton to a base. So as soon as I know what the reactants are and whether they're acids or bases, I can immediately predict the products of this reaction. HF needs to donate a proton, so HF loses an H plus and H2O gains an H plus. Another way of thinking about this is showing a picture of the reaction here in terms of starting with reactants, and now we'll show what happens as we go towards products. As this reaction proceeds, this H is transferred from the HF to the water. Now let's look at what happens coming back the other way. What happens if we think about the products here? These products, F minus, this is an equilibrium reaction, so this reaction go back to the left, the other direction. When that happens, F minus gains a proton from the H3O plus. That makes F minus a base. So F minus is the conjugate base because in this reverse reaction, F minus acts as a base, H3O plus acts as an acid, and we go back to these starting points. As a result, it's natural to use these terms. H2O is the base, HF is the acid, and as a result, H2O, once it's gained a proton, it becomes H3O plus, the conjugate acid. HF, once it's lost a proton, becomes F minus, the conjugate base. In the reverse reaction, it's always the conjugate base reacting with the conjugate acid to go back and form the normal base and acid on the left-hand side. Okay, so this is that same information, but just with the key terminology to write down. So an acid's conjugate base is just the acid after it's lost a proton, so it has one fewer H and a charge lower by 1. Similarly, a base's conjugate acid has one extra hydrogen atom and a charge higher by 1. When a reaction happens, when we find the acid on the left-hand side, its conjugate base is going to be one of the products. So the acid will lose an H plus to become F minus. The base, H2O, will gain an H plus to become H3O plus. And so this single sentence really describes what's going on in every Bronsted-Lowry acid-base reaction. The acid donates a proton to the base, creating the acid's conjugate base and the base's conjugate acid as the products. One of the next things we want to do is start to recognize those acids and their conjugate bases. So many of our acids have a hydrogen listed first in the formula, like hydrochloric acid or sulfuric acid. Another common feature is a COOH group in the chemical formula. So acetic acid and many other types of acids are like that. Another type of acid we can have is the conjugate acid of a base. So something like NH3 here is a very typical type of base. When we gain a proton, it becomes NH4 plus one extra H atom and a charge higher by 1. And so therefore, this is one of our types of acids. In the same way, these conjugate bases of the acids are some of our types of bases. Here's our first example using the definition of conjugate acid and base. Fill out the table below. Okay, so here's the solution here. CH3OH is an acid, so when we form the conjugate base, it loses a proton and its charge goes down by 1. Comes CH3O, and it was previously neutral, so now minus. The specific proton that we lost is this one right here. That OH proton can get deprotonated. That's the proton that we can lose. We never really lose hydrogens attached to carbons because that would put that negative formal charge on carbon, which is really unlikely and really unfavorable. We can put negative formal charges on oxygens. So there's the formula there. What about the next one? HCO3 minus. Again, it's the conjugate acid, so it needs to lose a proton. That's going to put CO3. It lost the hydrogen atom, and now the charge went down by 1, so from -1 to -2. The formula is something like this, so we've lost that OH, and now we have two oxygens with a negative formal charge on them in the CO3, 2- carbonate anion. CH3NH3 plus, this is a nitrogen with a positive formal charge on it, and so the natural hydrogen to lose is one of the hydrogens attached to the nitrogen. Leaves us with CH3NH, and now we lost one of these hydrogens, so it's just NH2. The charge was +1, it goes down by 1, so now it's just CH3NH2 neutral. And there's the Lewis structure. Again, key conceptual point that a nitrogen with a lone pair is a very common type of base. A nitrogen with 4 bonds and a positive formal charge is a very common type of acid. Or the last example, C5H5O-. So we can then turn that into the conjugate acid. So we need to gain a proton and have the charge increase by 1. So that becomes C6H5OH, gained a proton, and now the charge went from -1 back to neutral. There's the formula. The hydrogen had to attach to that negatively charged oxygen to form this molecule, which is called phenol. With that initial conceptual content out of the way, let's start to look at some of the mathematical parts of this. So water can act as both an acid and a base in water. That makes it an amphoteric species, if you want a large word for that. Therefore, anytime we're in water, this reaction is potentially occurring. This reaction is so important that it gets a special subscript, so the K equals Q expression here is labeled KW, and it's equal to, just as usual, since these are pure liquids, they don't show up in the equilibrium expression, so KW is equal to H3O plus times OH minus. Here's the value of it. It just turns out that at 25 Celsius, near room temperature, KW is almost exactly 10 to the -14. We can apply our normal equilibrium analysis to something like this. We don't normally do that, and we'll see why in a second. But in this case, for pure water, we can analyze that. We have no change in concentration here on the left because this is a pure liquid. We don't need to put anything in the ice table there. But for the products here, we start with 0 plus x of each, and we'll see that the k equals q expression. This is one of those cases where we don't need to approximate or anything like that. Just the trick of this being a perfect square will work. So since we get 10 to the minus 14 is equal to x squared, when we take the square root of both sides, we get 10 to the minus 7 molar is equal to x. And in general, the way we're going to solve this is not ever by making an ice table, but we're always going to plug right into kW is equal to h plus times OH minus. We'll know one of those, or H3O plus times OH minus, because we normally emphasize hydronium being H3O plus. Then, because we'll know one of those concentrations, we'll just be able to solve for the other without building a separate ice table for this reaction. According to really our Arrhenius definition of acids and bases, a solution is acidic if H3O plus is greater than OH minus. Remember, when we put an acid into water, it makes more H3O plus. And therefore, because there's this equilibrium, that means that mechanically the OH minus concentration decreases when we put an acid into water. The exact reverse thing happens for putting a base in water, and if it's neutral, we just have that same situation as we had before with H3O plus is equal to OH minus. The next conceptual point we have is pH. So this is review from high school or chemistry 110. The definition of pH is shown here. Negative log times H3O plus of H3O plus is the definition of pH. And again, if we remember our sort of logarithm type math, if I want to solve to go the other way here, all I have to do is move the negative to the left, so I get negative pH is equal to log of H3O plus. And to undo the logarithm, I have to take 10 to the power of both sides. So that gives us this equation over there. Sometimes we give you that equation, but you are expected to also be able to solve that one yourself by just using the properties of logarithms. So this is a log base 10. So to undo the logarithm, we use 10 to the power of. Just like earlier when we had a natural log, we took e to the power of to undo that. So our pure water we just showed has H2O plus equal to 1 times 10 to the minus 7 molar. The pH then is just negative log of H3O plus is equal to exactly 7.00. Remember what the logarithm is. The log base 10 of 10 to the minus 7 is equal to negative 7. So we have negative 7 times negative 1 is equal to 7.00. Note the units here, or note the significant figures here. The only figures that are significant in a pH are the ones after the decimal place. So we had 2 significant figures here. This is 2 significant figures here in our result as well. So here's some pHs of common substances. Note that pH can be negative or greater than 14. That would just be a concentration of H3O plus that's greater than 1 molar, or a concentration of OH minus that's greater than 1 molar. Most of our foods here are somewhat acidic. Blood, seawater, some other cleaning products and things like that, slightly basic. The next definition we're going to have is POH. So POH we define in the exact same way as pH. POH is negative log of OH minus, and therefore we can do that same trick of taking negative 10 to the exponent and get OH minus from the POH. The next thing, however, is that if we use our KW equilibrium and apply our logarithm rules here, we get this nice equation here that it turns out that at 25 Celsius, 14.00 is equal to the pH plus the POH. That can be a very nice way to solve problems because we might first calculate the concentration of OH minus, then turn that into a POH, and then if we look at this equation, if we just subtract pH from both sides, we can do something like 14.00 minus pH is equal to POH to solve for, POH if given pH, or vice versa, 14 minus POH is equal to pH. Okay, note that acidic, basic, and neutral solutions, if we're at 25 Celsius, these second things are true, that at 25 Celsius, an acidic solution is one that has a pH of less than 7, a basic solution is a one that has a pH of greater than 7, and vice versa, or the reverse for POH. POH less than 7 is acidic, is basic. POH greater than 7 is basic. Again, with the negative in that definition, if my pH is equal to 0, that means I actually have a very large concentration of H3O plus, because my H3O plus here is 10 to the minus 0 is equal to 1 molar. So the bigger the concentration of H3O plus, the smaller my pH is. And again, the same for reverse for bases. The more basic a solution is, the smaller the pOH and the greater the pH. Here's our first quantitative set of problems. You can use the equations on the previous slide to do these 4 example problems. So using these equations, let's see how we can get the concentration of OH minus. We're given hydronium ion concentration, that is H3O plus. To solve for OH minus, then our Kw equation will work well. We can we're at 25 Celsius here unless we state otherwise in this part of the class. So H3O plus is known. We want to solve for OH minus. Just divide both sides by H3O plus. In this case, we want pH, so the definition of pH will work. And 10 to the minus 7, so pH lower than 7. On this calculator, the 36, I have to tap this ln log button twice to get the log base 10, so to do that. And there's the solution. So that isn't that hard to do. I'm going to use that same definition of pH equation. pH is negative log of H3O plus. Now in this case, I want to use pH to get H3O plus, so I need to solve for H3O plus on both sides -1. Then I'll take 10 to the power of both sides. That will undo the logarithm and give me H3O plus on the right-hand side, and on the left-hand side 10. Then when I plug in, I go 10 to the negative 4.82 is what I need to type into my calculator to get the constant of H3O. Here's the final answer then. 10 to the minus 4.82 is 1.5 times 10 to the minus 5. Initially, again, in this TI-36, it doesn't convert this to scientific notation, so you can choose mode scientific notation, and then it will write it with the proper scientific notation, so you don't need to try to move the decimal place over that many places. Here's the last version, the OH minus ion concentration of this blood sample. What is the pH? So this will work out a couple of different ways. We're given OH minus, so we could first use OH minus to get H3O plus, and then use pH. I think it's maybe a little bit easier to first get OH minus and go to pOH, and then use pOH in this pH plus pOH is 14 equation, but both will work. I'll show the one I think is a little bit easier. That approach then, pOH is negative log 2.5 times 10 to the minus 7. Gives us pOH is 6.60, where this is our 2 significant figures. Next, we can go into the Kw equation. Because we're trying to find pH, we need to subtract pOH from both sides, which gives us 14 minus pOH is equal to pH, which is 7.40. Again, 2 significant figures after the decimal place, because when we're adding and subtracting, we keep to the same number of decimal places after the decimal. So 0.60, we keep to the 100th place here in our pH as well. Now that we know some of our quantitative information about calculating pH, let's look at the difference between strong and weak acids and bases. So this is the key initial distinction. In water, a strong acid or a strong base dissociates completely into its ions. The term from prior chemistry is that is a strong electrolyte. So something like HCl, we can think of it as existing entirely in aqueous solution as H plus and Cl minus ions. Same with NaOH, it dissociates fully into Na plus and OH minus ions. Admittedly, this isn't really any different than any other ionic compound. Remember, all ionic compounds are strong electrolytes and dissociate fully into ions in solution. So this isn't that unusual, but this is very unusual. HCl is a molecular compound. Typically things that are just molecular solids would stay together in solution, but strong acids will dissociate fully. On the other hand, neutral weak acids and bases only partially dissociate into ions. So something like vinegar, acetic acid shown here, CH3COH stays mainly CH3COH in solution. only a small amount of it reacts with water to make H3O plus and CH3COO minus ions. In a normal vinegar solution, that would be about 4% dissociated. Again, the term here is that it's a weak electrolyte. This distinction really drives how we're going to work with calculating pH and thinking about their properties in solution. Here, since we have a one-way arrow for strong acids and bases, we're just going to be able to use stoichiometry to figure out what's going on with these. On the other hand, for weak acids and weak bases, this equilibrium process, we're going to need to use our approach to solve for X to figure out the pH there, because we do have to worry about that equilibrium. So there's the list of polyatomic ions that you need to memorize for CHE120 that was provided back at the beginning of the class. This is definitely the time when you should know all of those because they show up in all these different acid-base compounds. So you're definitely responsible for knowing these, and therefore knowing that, again, when you see these ions, these are what are going to go into water, and these are the ions that we're going to worry about figuring out their acid-base properties. So with our strong acids and strong bases, first acids, for strong and weak acids, we have a couple ways to look at those. First, for strong acids, there are 6 common strong acids that we're going to worry about in this class, shown in this list, and just memorize those. All the other acids we work with are weak. So again, for these 6, when it goes into water, it quantitatively makes H3O plus ions, and again, this is an acid, so what's the other product? The conjugate base. The other really important thing here is because of this one-way equilibrium arrow, that implies that going the other way, this reaction doesn't happen. The reverse reaction, where Cl- would react with H3O plus to go back and make HCl, doesn't happen, and therefore Cl- is an incredibly weak base. So this we call an ineffective base, all these conjugate bases of strong acids. Same thing with strong bases. For strong bases, it's a little bit more complicated. We have this definition. Metal hydroxides are metal oxides, where the metals are going to come from groups 1, 2, and 3. So again, that's based on the the column of the periodic table, group 1, group 2, and then across the transition metals, group 3. So you look for metals from that group along with, again, an oxide, that's an O2 minus anion, and hydroxide, remember one of your polyatomic ions to know, OH minus. So these are these ionic compounds, and these ionic compounds happen to dissociate fully and act as strong bases. They quantitatively make OH minus ions. So if I put 1 molar NaOH in solution, it's going to make 1 molar Na plus ions and 1 molar OH minus ions in solution. For BaOH2 here, because of the 2, 1 molar BaOH2 would actually make 2 molar OH minus ions in solution, again because of that coefficient of 2. The one caveat, or the one that's a little bit more difficult to understand, is an oxide. So these are both hydroxide ions. For an oxide, in principle, the thing that would happen would be this. We'll just show this in sort of a two-step process. First thing that would happen would be Li2O solid would just dissociate into, since there's 2 Li ions, that's going to be 2 Li plus an O2 minus ion. Again, these would be aqueous. But now, once we have this O2 minus ion, this is an incredibly strong base. This is an oxygen with a 2 minus formal charge and no bonds. That's incredibly unstable, and so immediately this O2 minus that you make reacts with water. So then the O2 minus reacts with water, and this is an acid-base reaction. O2 minus is the base, and what does it do? It's going to take a proton from H2O, because that's what any base does, and make 2 OH minus ions. And so the net effect of these two steps, when we put an oxide in water, is what's shown here. So the net effect is each Li2O that goes into water, it first dissociates, but then the O2 minus, each one O2 minus that goes into solution actually makes 2 OH minus ions. That's what we're sort of showing here. One OH minus makes one O2 minus makes 2 OH minus. And therefore, when we put an oxide into water, we're going to show the oxide reacting with water, and therefore making 2 Li plus and 2OH minus. So the cation just goes into solution like normal, but the oxygen, each oxygen reacts with one water to make 2OH minus ions. Note, however, that here, a common mistake people will make is that for the hydroxides, they'll try to show the hydroxides react with water. That's not what happens. For hydroxides, it's just dissociating into ions. That's always the first thing we need to think about, is when an ionic compound goes into water, it dissociates into its ions. And then we think about the acid-base properties of those ions. So OH minus is our strong base. That's why NaOH is a strong base. We'll see when we put other ions into water, we'll also need to think about their acid-base properties. Now that we've spent a lot of time thinking about strong and weak acids and bases, their properties, and how we can identify them, let's go into the actually calculating the pH. That's generally sort of a little bit of the easier part. So let's think about the pH of 3.6 times 10 to the minus 5 molar HNO3. HNO3 is a strong acid. Strong acids, the thing you need to know about them is that they completely dissociate into their ions. So in this case, this reaction occurs 100%. It goes to completion. Note the one-way forward arrow here. Each HNO3 in water reacts with one H2O molecule to make one HNO3 plus and one NO3 minus ion. Because the stoichiometry here is 1 to 1 and this reaction goes to completion, 3.6 times 10 to the minus 5 molar HNO3 means that your final equilibrium concentration of H3O plus is also 3.6 times 10 to the minus 5 because of this 1 to 1 stoichiometry, and that the reaction goes to completion. In this case then, the pH is just negative log of H3O plus, which gives us 4.44. This should make sense. We have a acid, so the pH should be lower than 7. 4.44 is a bit lower than 7. This is a quite dilute acid, so the pH isn't that much lower than 7, but that is the final solution. So for these strong acids and strong bases, we don't need to use any of our new equilibrium information, ice tables, solve for X. It's just a normal stoichiometry problem like you've done in Chemistry 110 or high school. A strong base is going to work in the same way, where we just need to use stoichiometry to get the pH. So let's look at 1.7 times 10 to the minus 4 molar Na2O. Since it's a strong base, it will react completely. Now this is that slightly trickier version where each of those O ions reacts with a single water molecule to make two OH minus ions. So the final balanced reaction is Na2O plus water goes to 2Na plus 2 OH minus ions, where that's the key fact to remember, is each oxygen here is going to make 2 OH minus ions in solution. Now we're ready to calculate this. Again, we have the same one-way equilibrium arrow, or one-way forward reaction arrow. Therefore, we can directly calculate the concentration of not H0 plus, but in this case OH minus, right? Bases make OH minus. So we can calculate that here to get the amount of OH minus. So to get that concentration, I can start from the concentration of the Na2O, 1.7 times 10 to the minus 4 molar Na2O, but I want the concentration of OH minus, so I'll do a stoichiometry conversion on that. So times 2 OH minus, or 2 moles of OH minus for every 1 mole of Na2O. That then cancels things appropriately and just shows us that the concentration of OH minus is exactly double the concentration of the Na2O that I put in the solution. Strong bases in general have this property where we might make 2 or 3 OH minus ions in solution for every 1 of the strong bases we put in solution. So always pay attention to that stoichiometry step first. In this case, we get 3.4 times 10 to the minus 4 molar OH minus. Now we can rely a little bit on what we did earlier. A lot of ways to get from concentration of OH minus back to pH, but I think an easy way to do that is using our equation sheet to first get POH. So POH is negative log of OH minus. The first step there gives me 3.47. Next, to get to pH, 14.00 is equal to pH plus POH off our equation sheet at 25 Celsius. So we can do 14, again we want pH, so it's going to be subtract POH from both sides, so 14 minus POH is equal to pH is equal to 14 minus 3.47 is equal to 10.53. Here's the calculator piece of it. Again, we get 2 sig figs here initially, so 2 numbers after the decimal place in our POH, and then again also in pH. Therefore, 10.53 is the final result, and that makes sense because, again, it's a base, so pH needs to be greater than 7. 10.53 fits nicely. Some mistakes that people make is they just forget to convert from POH back to pH, but you should be able to identify that mistake if you recognize, hey, pH equals 3.47 makes no sense because that would be an acid, and this is a strong base, so the pH definitely needs to be greater than 7. This is the end of that first bit of acid-base content. Key things to know are on this slide. An acid-base reaction is always a proton transferred from the acid to the base, therefore making the conjugate acid and the conjugate base. So you should be able to identify conjugate acids and bases in a reaction, as well as, if you're given a particular substance, write its conjugate acids or bases. Then you should also be able to do these calculations for strong acid and strong base pHs, all just based on stoichiometry and using the provided equations. Again, start memorizing these strong acids and strong bases now so that you can deal with them once we start mixing in weak acids and weak bases. We've dealt with strong acids and bases. What happens if we put a weak acid or base into water? Well, weak acids and bases, according to their definitions, our content from earlier that we know, is that these are going to dissociate partially. What does that mean? That means that when we put them into water, mainly they stick together. So HA mainly just sits there as HA, but it is an acid, so it can react with a base. The only base that's present in pure water is just water. Water is amphoteric. It can act as a base or an acid. So when HA reacts with water, the acid is going to donate a proton to the base. So therefore the products are the acid lost a proton, the water gained a proton, so we make H3O plus, the conjugate acid of H2O, and A minus, the conjugate base of HA. Now again, because for a weak acid we know it dissociates partially, that means the value of the equilibrium constant here is less than 1, and usually much, much less than 1. The equilibrium lies towards reactants. Again, that key information about our number line, where if we look at this here, if we were all reactants, that would be a K very, very close to 0. All products would be a K much, much greater than 1. Weak acids only dissociate partially, so equilibrium definitely favors reactants by quite a bit. Equilibrium constant, products to their coefficients over reactants, so H3O plus times A minus over HA. H2O is a pure liquid, so its concentration doesn't change as we run this reaction. Doesn't show up in the K equals Q expression. Now a weak base dissociates partially as well. So when the base goes into water, a base, what it does is it accepts a proton from an acid. The only acid around is water, H2O. The base can accept a proton from water. That turns the base into its conjugate acid, Hb+, and water was the acid, so it donated a proton, leaving behind OH-. This agrees with our definition. Acids produce H3O+, bases produce OH- in water. In just the same way, since it's only dissociating partially, that means equilibrium favors reactants. That means Kb, the name we give for this equilibrium constant, Ka for acid, Kb for base, is much less than 1, or is less than 1 and usually much less than 1, because equilibrium is going to favor reactants, so K is going to be pretty small. Equals Q expression looks the exact same as it would normally would. Kb is equal to OH- times Hb over B, where water, again, as a pure liquid, doesn't show up in the expression. Another thing we can do, just looking at these reactions, is categorize weak acids and bases by their strength. Even though we call them all weak, there's a wide range of strengths of weak acid. Again, weak is that medium strength type of acid. So some weak acids are pretty strong, some weak acids are pretty weak. It covers a pretty wide range. Which weak acids are going to be stronger? Well, a stronger acid is going to make more H3O plus in water. And so a stronger acid, if we look at the K equals Q expression here, how do I make more H3O plus in water for, let's say, the same concentration? I need to have Ka get bigger, right? The bigger my Ka is, the more this reaction favors products, and therefore the stronger the acid. As shown on this slide, the larger the Ka, the stronger the weak acid. So here's a bunch of different Kas for weak acids. You always get a table like this on the quizzes and on the exams, and this also gives you a really good way to identify weak acids. If you're not sure if something is a weak acid, just look it up on this table to find its Ka, and that's a good way to verify that yes, this is in fact a weak acid, right? HF is a weak acid, whereas HCl doesn't show up on this chart because it's a strong acid. Okay, our next little exercise here, rank the following acids from strongest to weakest. So again, the key information, the larger the Ka, the stronger the acid. So if I look at this here, the biggest Ka is down here at the bottom. So this has a ranking of 1. 3.0 times 10 to the minus 4 is the biggest, right? 10 to the minus 5 is a smaller number because it's a more negative exponent. Then second is HCOOH, that's the second strongest, and CH3COOH is the third strongest, or the weakest of these three acids. The larger the value of Ka, the stronger the acid, the farther the equilibrium lies to the right, and therefore the more H3O plus is produced for a given concentration. So if I had 1 molar solutions of each of these three, this would have the most H3O plus, and CH3COH would have the least H3O plus produced. When we think about pH, this would have the lowest pH because it has the most concentration of H3O plus. This would have the highest pH. So we can ask these conceptual questions in a lot of different ways if you can just keep straight the meaning of the Ka and how that affects the concentration of H3O plus and the pH of the solution. Same idea works for Kb. The larger the Kb, the stronger the weak base. We'll notice that all these weak bases have nitrogens in them, and these nitrogens also have a lone pair. That lone pair is how they're going to be able to accept a proton and form the conjugate acids. The conjugate acids here are all nitrogens with a positive formal charge, or with a positive overall charge on the molecule after they've picked up a hydrogen. And these are all of these cations shown on the right, ammonium and so forth. So how do we calculate the concentration of a weak acid or a weak base? Well, that Ka or Kb equilibrium that we just wrote down is exactly how we do it. So if we want to know the pH of a 0.015 molar solution of formic acid, the first thing we have to recognize is that this is a weak acid. It has acid in its name, and it's not one of our 6 strong acids, so this is in fact a weak acid. Then we go through our normal equilibrium steps. Remember, the first thing we need is a balanced equation, K equals Q expression. For this first one, I'm going to show this with the slides here. So it's a weak acid. Therefore, the thing you need to memorize is that when a weak acid goes into water, the Ka reaction is what happens. So the weak acid reacts with water to make H3O plus and its conjugate base. So we'll substitute in for our weak acid HCOOH. That's our weak acid. And then the water part is always the same, but the A minus, right, that's the conjugate base of the weak acid. So instead of A minus, we have HCOO minus, the conjugate base of formic acid. So that's our balanced equation. Next, we need to write out K equals Q. So for this type of reaction, again, the K is a Ka, and we look up formic acid in our table of weak acid Ka dissociation constants. We find that it's 1.8 times 10 to the minus 4. Then we can write out our equilibrium expression. So Ka equals Q. Ka is 1.8 times 10 to the minus 4. Q is equal to products H3O plus, HCOO minus over reactants HCOOH. Next, we're on to step 1, filling out the ice table. So the given information was 0.015 molar HCOOH. That's what's known as the analytical concentration, so that is our initial concentration in our ice table. So 0.015. Again, we're all in molar here. I'm going to write out our ice table, just add these lines. H2O is a pure liquid, so its concentration doesn't change. Next, H3O plus and HCOO minus both started at 0. Now the change here, again, we could think about K versus Q, but we started with no products, so we're going to have to form a little bit of each of these products. So this is going to be plus, and the coefficients are all 1, so just plus x for the products. The reactants, we have to use up a little bit of reactant, so minus x. Again, all coefficients are 1. Then equilibrium, we have 0.015 minus x, and x. Next step is to substitute back into our K equals Q expression and choose a method to solve. So substituting in, we have 1.8 times 10 to the minus 4 is equal to H3O plus at equilibrium is equal to x, so x times x over 0.015 minus x. That's HCOH at equilibrium. Now we can choose a method to solve. So if we look at our value here, 1.8 times 10 to the minus 4 is our value of k. That is less than 10 to the minus third. And so that small x approximation would be a pretty good idea here. That will just simplify our math here. Again, the small x approximation is going to assume that 0.015 minus x is about equal to 0.015. This makes sense. Our assumption, or the general picture of a weak acid, is that it mainly sticks at reactants, and so we're going to guess that most of our HCOOH stays present at the reactants, and only a little bit of it dissociates into H3O plus and HCOO minus. That lets us approximate at 1.8 times 10 to the minus 4 is approximately x squared over 0.015. To solve here, I'm going to multiply both sides by 0.015. So 0.015 times 1.8 times 10 to the minus 4 is equal to x squared. Then take the square root of both sides to get my value of x. I find x is equal to 0.00164. And now I need to do my 5% rule check, as I always do when I make that small x approximation. So is x less than 5% of the thing I ignored, right? I assumed 0.015 minus x was about 0.015. Is that a good assumption? Well, 5% of 0.015 is 0.00075 molar. And our x is 0.00164. So that approximation failed. 0.00164 is a bit bigger than 0.00075. I'm at the point where, since the approximation failed, I need to fix it and get a correct answer. Successive approximations is a good idea here. So if I do successive approximations, the idea with successive approximations is, okay, I ignored the x. Let's bring that x back. Then when I go back into here, in my square root here, this is now, we turn this into 0.015 minus x, let's say like 0 or x1 or something like that. The idea is that I'm going to keep guessing. So this was 0.015 minus x0. My initial guess was x0 equals to 0. Now this 0.00164 molar is my first guess, x1. And the idea is now I just keep taking that same guess and updating it. So the next guess I'm going to make is square root of 0.015 minus x1 times 1.8 times 10 to the minus 4. And this would give me my next value of x, x2. Here's the solution. X, again, you could just type this in like this as well, but I think sometimes it's convenient to have it in the variable. So I stored this previous solution to the variable x using my store and x key, and then I have my square root 0.015 minus x times 1.8 times 10 to the minus 4, and that gave me my new value of x. Now I could store that and keep going, but in this case, actually, if I look at it, I only have 2 sig figs in my answer, so I'm going to have to round this eventually to 2 sig figs, and to within 2 sig figs, I get 0.0016 molar for both. X1 was 0.0016 molar, and X2 was also 0.0016 molar. And so I am justified in stopping at this point. Or again, I could do one more cycle, but this is fine to stop and basically now get to the final answer. Say, okay, H3O plus is equal to, right, remember the next step here is to plug in to my E row to calculate what I need. So my H3O plus is equal to X is equal to 0.00155 molar. And then I can take negative log of H3O plus to get my pH, which is equal to 2.81. Now you might get slightly different answers depending on rounding, but yeah, about 2.81 for my pH. That makes sense because this is a weak acid, so the pH is lower than 7. Ka is pretty large for a weak acid. The range of Kas for weak acids ranges from a maximum of about 1 to a minimum of about 10 to the minus 14. So this is actually a pretty big Ka. Again, if I wanted to do another check, I could plug back into K equals Q, plug in my 0.00155 squared over 0.015 minus X. Here I get 1.79 times 10 to the minus 4 when I do that, and that, yeah, agrees pretty nicely with my value of K, 1.8 times 10 to the minus 4. Another approach, once you recognize that your approximation didn't work, would just be to switch back to quadratic or solver. In this case, quadratic itself isn't even that bad with the number of terms here. Pretty fast to do quadratic as well, but of course solver is also really fast and easy. Type my equation in for this solver. I don't need to set anything equal to 0, just left-hand side is equal to right-hand side. Again, remember we need a good guess, so x equals 0. Click solve for x, and there's our solution, 0.00155. The solution does get stored to the variable x, so I can go in and use that to calculate my pH, which matches with successive approximations. Also pretty fast to go in and check with K equals Q, just retype in x squared over 0.015 minus x, which agrees as well. For this problem, the pH of a weak base, see if you can apply the Kb equation on your own. K equals Q, go through all the steps to solve for x and therefore the pH. And if not, I'll show you my solution in a second here. Okay, so the same equilibrium steps as normal, where the first thing we're going to need is our balanced equation. In this case, for a weak base, that's going to be the Kb reaction. So it'll be normally just some sort of base B. In this case, I'm not going to swap that out for this particular base because it's just sort of a long formula that is just going to be harder to write. So I'll just call this whole thing some generic weak base B. That's perfectly fine in this case, plus H2O. If we were just asked to write out the Kb reaction, we'd have to plug this in. But for the purpose of solving for the equilibrium concentrations, it won't really matter. Then again, the products here, this is a base, so it reacts with water. That's the only other thing in water. And the products have to be, the base is going to accept a proton from the acid. So the products are the conjugate acid, and OH minus is the conjugate base of water. Acid, base, acid lost a proton, base gained a proton. The same as the generic Kb reaction. K equals Q, we may as well write that. So since this is a base protonation reaction, its Kb is equal to Q, so that's 3.2 times 10 to the minus 10 is equal to Hb plus times OH minus over B. The next step is our ICE table, so ICE. We're in the normal concentration units, or it should be in molarity. Water is a pure liquid, so it doesn't have a concentration that changes. The initial concentration of reactant of the base is 0.5 molar, so 0.50. We start with none of the products. Because we started with none of the products, we're going to make a little bit of products to get to equilibrium. So plus x, all the coefficients happen to be 1. We're going to lose a little bit of the reactants, and our equilibrium is xx 0.5 minus x. Then we're on to step 2, which is to plug into our K equals Q expression and then choose a method to solve. So we'll plug in 3.2 times 10 to the minus 10 is equal to x times x over 0.5 minus x. That's plugging into K equals Q. Now, what method is going to be best to solve here? Well, K is incredibly small. Remember, the smaller that K is, the more equilibrium lies towards reactants. So here we expect equilibrium to lie almost completely towards reactants. X should be very, very, very small. And so the small x approximation makes sense. So we'll approximate 0.5 minus x is approximately 0.5. When we do that, we get 3.2 times 10 to the minus 10 is approximately x squared over 0.5. Now we have simplified our math significantly. Multiply both sides by 0.5. That's equal to, on the right-hand side, x squared. Take the square root of both sides, and we get x is equal to, we get 1.26 times 10 to the minus 5th molar, coming right out of that math. This is annoying with all these significant figures, so you can use the mode button to switch it to scientific notation and not have to worry about that exponent. Since we approximated, we should check our answer. Is x less than 5% of the thing we ignored? So 5% of 0.5 molar, that was the large concentration we were ignoring. Is x less than 0.025 molar? Definitely. Way, way, way less. This is, again, you can see all those zeros there. Much less than 0.025, and so our approximation is valid, and we can go to the final step of calculating pH. In this case, because from the ice table we get OH minus, there's that extra step. First, use OH minus from the ice table, 1.26 times 10 to the minus 5. Then we can calculate POH to get POH is 4.9. pH plus POH is 14. So if I take 14 minus POH, subtracting from both sides here, I'll get to pH, and that gives me a pH of 9.1. Always check that that makes sense. In this case, yes, our pH is greater than 7 because we have a base. It's not much greater than 7 because even though it's quite a concentrated weak base, it's a weak base, and it's a very, very weak base because Kb is so small. So that's why the pH is only slightly greater than 7. Okay, so a really important sort of summary chart that you should be developing. This is something that might be useful to be writing out on your homework, writing out in your notes, to sort of categorize the acid-base behavior that we have. So far we've identified the fact that we have strong acids, and so the way this chart works is we've got our strong acids up here on the top left. 6 common strong acids, and you need to just memorize those. Now, again, on the other side here are going to be bases. So this is basically, you can view this over here as the conjugate base. So because we have those strong acids, by definition, we know they're conjugate bases, right? The conjugate base, remove a hydrogen and decrease the charge by 1. So the conjugate bases are Cl minus, Br minus, I minus, NO3 minus, ClO4 minus, and HSO4 minus. These are the conjugate bases of our strong acids, and remember the way this chart works is that the stronger the acid is over here, the weaker the conjugate base. That's one of our key concepts in this part of the class. So what we have over here is what we call ineffective bases. This is something that doesn't affect the pH. If we go down to the bottom of our chart now, over here we have strong bases. So this is our definition of strong base. Here's some examples. Hydroxides with OH minus ions and a metal in them. Oxides with an O minus and again a metal in them. And again, these are our strongest possible bases. Now we're going to cheat a little bit going this direction. Here we're not going to have the actual conjugate acids here. The conjugate acid of these would basically just be water. But here we'll just say the cations from those strong bases. Things like, again, any group 1, 2, or 3 cation, Li plus, Na plus, K plus, and so forth, Ca2 plus, Ba2 plus. These are all of what we'll call our ineffective acids. So these things don't affect the pH at all as well. If you look at the compounds you've used in lab so far, we use these ineffective acids and these ineffective bases in lab a lot of different times. Maybe I want to get a negatively charged ion into solution, So we're going to pair that with one of these ineffective acids to get it into solution. Similarly, if I want to get a positive ion into solution, a good thing to pair it with is one of these ineffective bases. I don't want to, when I'm just trying to get one ion into solution, have the other ion introduce a lot of acid-base chemistry into the solution that I don't care about or I'm not interested in. So really, really commonly used. In the middle of this picture, and what occupies the most space here, are our weak acids and weak bases. So in here we have weak acids on the left. On the right we have weak bases. When you hear weak, you should really think of that as being like medium strength. Sometimes people will think that a weak acid's base should be, conjugate base should be a strong base, or a weak base's conjugate acid should be a strong acid, but we'll see that's not the case. Weak really means medium strength, and so weak acids' conjugate bases are weak bases. And this arrow shows us that the stronger the weak acid, the weaker the conjugate weak base. Similarly, if I have a pretty strong weak base, its conjugate acid is going to be one of our weakest weak acids. Again, a little bit confusing the terminology, but if you think about weak as meaning medium strength, that's a useful way to do this. So next what we'll do is we'll start to fill in what these common weak acids and weak bases are. Again, there's vast numbers of these that we'll fill in, but they do fit into a bunch of common categories. So let's look at the Lewis dot structures of these here. For our strong acids, the strong acids fit into two categories. Halogens, so all of the halogens except HF are strong acids, so HCl, HBr, HI. The other strong acids are these oxyacids, so they're an electronegative atom like nitrogen, chlorine, or sulfur bonded to as many oxygens as possible, and that will make our strong acid. So this is nitric acid, HNO3, perchloric acid, HClO4, and sulfuric acid, H2SO4. With all of these oxygens in the Lewis structure, as soon as we deprotonate and make the conjugate base, the conjugate base here is going to be really well stabilized by resonance among that those different dot structures. So something like NO3 here, once I, there's no, that's a bad structure. There's no lone pair on nitrogen there. NO3 minus looks something like this. And we can see that there's these negative formal charges that can move around into different structures. The same thing with when we look at ClO4 minus, we'll have the ability for the negative formal charges to move between different oxygen atoms to stabilize them. Now, the other types of weak acids here, one very common type of weak acid is something with a COOH group. That's a carboxylic acid. So vinegar, our stereotype example of a weak acid, or acetic acid, is one of those. Many others, many drug molecules, the proteins in your body, your amino acids, have these COOH groups as well. Again, the acidic hydrogen is this one right here, because once it deprotonates, we'll get something that looks like this, with, again, a negative formal charge that can be shared between multiple oxygen atoms, and that makes this a relatively stable conjugate base. We also have some of these other types of weak acids, so just a neutral thing with a hydrogen first in the formula is another common type of weak acid, so like HCN, HOCl. Note that all of these neutral weak acids are molecular compounds, so these are all sort of molecular solids, and the best way to deal with these or think about them is to look up in your table. We'll give you a table of weak acids, and so you can look up these weak acids in your data tables. Now, the other type of weak acid that we have is a cation of a nitrogen base. So this is actually the conjugate acid of a weak base. So things like NH4+, really just any nitrogen with a positive formal charge on it, is our other type of weak acid. Likewise, if we think about the dot structures of weak bases, the weak bases are just the conjugate bases of the three common types of weak acids that we dealt with on the previous slide. So F-, that's the conjugate base of HF. HF loses that proton and becomes F-, its conjugate base. Similarly, HCN loses the proton to become Cn- here. The carboxylic acids, again, they lose their proton to become HCOO-. So these are many of your types of weak acids in water. These anions tend to be weak bases. And the other type of neutral weak bases are your nitrogen bases. So things with a nitrogen with a lone pair on it. That lone pair could bond to an H plus and make a nitrogen with a positive formal charge. Positive formal charge isn't perfect for nitrogen, but it's possible, and it occurs in those cations that we looked at on the previous slide. So here, NH3 can react with an H plus to make NH4 plus, which will have that positive formal charge on nitrogen. So yeah, anytime you see a nitrogen with a lone pair in one of these neutral molecules, you should suspect that that's going to be a base. Again, the best way to identify these weak acids is to look in your table of Kas for the conjugate acid. Here, the best way to find these weak bases is to look in, we'll have a table of the Kb for base equilibrium constants. If it's in there, it's a weak base. So filling those into our table, our weak acids can contain things with a COOH group, carboxylic acids, many of just these small molecules that have a hydrogen in them, so HCN, HF, many other of these sort of small molecules. And the third common type is a nitrogen with a positive formal charge. Then when we go across to the other side here, the common weak bases are just the conjugate bases of these weak acids. So here, something with a COO-, again, a very common one that we'll work with is acetic acid, CH3COOH. Its conjugate base is CH3COO-. That's one common example. And again, if we look at each of these weak acids here, we can make it their conjugate bases. So these anions, CN-, F-, etc. All of those are common types of weak bases. Again, the one neutral type of weak base is a nitrogen-containing compound, so something like RN with a lone pair. Again, a very common example here would be NH4 plus as the conjugate acid, and NH3 ammonia, which again has that nitrogen with a lone pair on it. In terms of how to use this chart, again, you need to memorize strong bases, strong acids, and therefore once you memorize those, you also sort of for free get the conjugate bases of strong acids, which are those ineffective bases, which are, by default memorized since you just take a proton off of each of the strong acids. The same thing here. Once you know this definition of strong bases, the cations are just the positive ions. Group 1, 2, and 3 metals are your ineffective acids. We'll see later that the weak acids and weak bases will have data tables that will contain big lists of those with the appropriate information you need. So memorize strong acids, strong bases, these corners of the chart, and use your tables for the middle. So let's take a minute to do this exercise. Are each of these following solutions acidic, basic, or neutral? So when we come to the exam, you're going to have to do this without, right? The only thing you'll get are the data tables. But for a lot of these, you can just have them sort of by memorization. So HI is one of your memorized strong acids. So this is acidic. And for strong, weak, I'm just going to abbreviate SA is equal to strong acid and so forth. So this is a strong acid. LiOH, this is a group 1 metal with a hydroxide anion. Remember, our definition is that it's group 1, 2, and 3 metal cations with hydroxide or oxide anions. So this meets that definition of a strong base. So basic solution, and this is in fact a strong base. CH3COOH, that is a not one of our 6 common strong acids. If we just look at the formula, we'll be able to look at it and see that it has that COOH group. That is a carboxylic acid, which is a common type of weak acid. The other thing we'll be able to do is look this up in your data table. So if you look at your data table, table of Ka does contain CH3COOH. So we'll be able to look up there, find acetic acid in it, and therefore verify that this is acidic and in fact a weak acid, where WA represents weak acid, just some shorthand here. Okay, DNaCl. This is our first case of an ionic compound to worry about here. So let's think about what goes on with this. NaCl doesn't fit any of our categories really on its own. The first thing with this that we need to recognize is that this is ionic. Note that LiOH was ionic as well, but it just fit our category of a strong base. NaCl doesn't fit our category of a strong base. It has an Na ion, but it doesn't have a hydroxide or oxide anion. It has a chloride anion. Hi was molecular solid. CH3COH was also a molecular solid. But since NaCl is ionic, the first thing we're going to need to do with it is dissociate it into its ions. And think about the properties of those ions. So the two ions that this makes in solution are Na plus and Cl minus. Now we think about the acid-base properties of each of those. Na plus is a group 1 cation. That makes it an ineffective acid, and so it doesn't affect the pH in any way. Cl minus is an anion. We should suspect that this might be a base. But if we had memorized our list of strong acids, we know that the conjugate acid here is equal to HCl. HCl is a strong acid, which means by definition, according to our table on the previous slide, Cl minus is one of our ineffective bases. So this doesn't affect the pH either. Therefore, NaCl doesn't have any acids or any effective bases. Again, Cl minus is the conjugate base of HCl, but it's an ineffective base, so this is a neutral solution. Neither of these ions affects the acid or affects the pH of the solution. For E, this is back to being just a normal sort of molecular solid. And for this one here, we have a normal molecular solid, NH3 aqueous, so it just sticks together in the solution. And then we think about the properties of NH3. This is not a strong base, but if we think about its Lewis structure, it's a nitrogen with a lone pair on it. That is a common type of weak base because this lone pair could accept a hydrogen. A base is a hydrogen atom or a proton acceptor. So this can accept a proton, and therefore this is a basic solution, with NH3 being our very common type of weak base. This sort of analysis is often the hardest part of this equilibrium section of the exam, or just the acid-base section of the exam, because it really, as we've seen in our analysis here, really relies on that prior chemistry knowledge. You need to memorize the things you need to memorize, and then apply our rules for, okay, ionic things have to dissociate into ions. Molecular solids just generally stay together in the solution. So we need to really be able to rely on that prior chemistry from high school 110 and even earlier in the semester when we did these different types of solids. It turns out there's a specific mathematical relationship between the strength of an acid and the strength of its conjugate base. By manipulating the Ka and Kb reactions, we can see that adding the two reactions gives us the Kw reaction. So in this case, when we do that, we can see that Ka times Kb, so Ka for a weak acid times Kb for its conjugate weak base, is equal to Kw, which is our 10 to the minus 14 at 25 Celsius. So that lets us figure out all those compounds that aren't present in our table. In our tables of Ka and Kb, we can find things like acetic acid, CH3COH has a Ka. Similarly, in our table of Kb, we can find something like NH3. To get the related constants, to get something like CH3COO minus, that's the weak base, conjugate base of CH3OOH, I can find that by taking Ka for CH3COH and then using this equation to solve for the Kb. Same thing, but in reverse for NH3. If I want to know the Ka for its conjugate acid, NH4+, I can plug into this equation using the known Kb for NH3. Key conceptual point, the stronger the acid, the weaker the conjugate base. Let's use that new equation to answer this question. So first, which acid has the strongest conjugate base? We can either use the concept or the equation. The strongest conjugate base means I need to be looking for the weakest acid. the weakest acid that is going to be the one with the smallest Ka, because the bigger Ka, the stronger the acid, the smaller Ka, the weaker the acid. That means that the weakest acid is right here, CH3COOH, that's the smallest Ka. That therefore means that the acid that has the strongest the acid that has the strongest conjugate base is acetic acid, and its conjugate base is CH3COO-, just subtracting a hydrogen and reducing the charge by 1. Then writing the Kb for this reaction, that requires the math here. So the math is Kw is 10 to the minus 14 is equal to Ka times Kb. We know Ka, we need to solve for Kb, so divide both sides by Ka. 10 to the minus 14 over Ka is 1.84 times 10 to the minus 5 is equal to Kb is equal to 5.43 times 10 to the minus 10. That answer should make sense. 10 to the minus 14. The exponent here is negative 5, so negative 14 minus negative 5 gives us around 10 to the minus 9. And when you account for this 1 divided by 1.84, 10 to the minus 10 there, all checks out. This is that same explanation in text for you to read if desired. The next piece of information is polyprotic acids. So when you look at your tables of acids and bases, there's also many different acids that have multiple protons that can be ionized or protons that can be removed. So we have a separate table with these, and how this table works is something like carbonic acid, H2CO3, tells us that there's two acidic protons. Ka1, that is the Ka to remove the first proton. So if I'm thinking about a reaction like this, H2CO3, aqueous plus water goes to HCO3 minus plus H3O plus. That is the acid dissociation reaction for H2CO3, and that is Ka1. So this is the first one there, Ka1. Now I can also write an acid dissociation reaction for HCO3 minus. This product there, HCO3 minus, still has an acidic proton, so that could react with water and make, again, H3O plus and the conjugate base. That Ka is in this table as well. That's what this one is. The second one here, this is basically what Ka2 means, is this is the acid dissociation constant to remove the second proton. So it's this Ka. In the blue is down here. One thing to note here is sulfuric acid is in this table because while the first proton in sulfuric acid is a strong acid, the second proton, removing the proton from HSO4 minus, is a weak acid. So that one comes off. It's quite a strong weak acid, but it is still a weak acid there. So that's where you can find the Ka for HSO4 minus. Some conceptual points about these polyprotic acids. So notice that the first H plus here, the first proton, is the easiest one to remove. That's the one that has the largest Ka. As we keep removing more and more protons, we build up more and more negative charge on the molecule. That's more and more disfavorable. Harder and harder to stabilize that negative charge when we've got 2 or 3 negative formal charges right next to each other in the molecule. The other key fact is that these middle compounds act as both acids and bases. So H2PO4 minus could act as an acid, as shown in this equation, or since it's the conjugate base of a weak acid, this is also a type of a weak base as well. And so, again, we could also write that and think about that in terms of its basic properties. This is really useful for making different types of buffers and solutions in water. The special name for this type of compound that has properties of both acids and bases is amphoteric. So there is the word, some nice Greek roots there again. So an example, something like HCO3 minus can act as both an acid and a base. In this case, it turns out that the acid here is pretty weak. HCO3 minus has a very small Ka. It has a slightly bigger Kb. So when we just put HCO3 minus in water, it ends up acting a little bit better as a base compared to as an acid. And so a solution of pure HCO3 minus is actually slightly basic. One more conceptual point on acid-base chemistry. One way to think about an acid-base reaction is that it's a competition for a proton. So this type of reaction with just a generic acid and base, none of these are water, we can think about it as put the two conjugate bases on either side and they're playing tug of war for this proton. Who's going to win the fight for that proton? Well, the stronger base is going to win the fight and get the proton. That's what being a stronger base means, is that it's better able to act as a base. So in this case, whichever one of these is a stronger base is going to get the proton. And what that's going to mean is that when the stronger base, let's say it's NH3, when NH3 gets the proton, that means that it's going to push this reaction to the left towards NH4 plus and CN minus. These are the weaker acid and the weaker base. Same idea with if you thought about it as a competition to donate hydrogens. In this case, HCN would be the stronger weak acid, and it's going to sort of win the fight and push this reaction back towards reactants. So it's always the weaker acid and the weaker base that sort of are where equilibrium lie. In this case, for this problem, it turns out that NH3 is a slightly stronger base, and similarly, HCN is a slightly stronger acid. So this is a slightly stronger base. It wins the fight for the proton, which means equilibrium favors reactants, and we end up with these as well. Here is our overall summary information of weak acids and bases. Another view of that key information about identifying strong, weak, and ineffective acids and bases. This is really going to be the key skill going forward that we'll need to solve different types of acid-base chemistry problems.